Hello, this is the first video of Chapter 9. Chapter 9 is a very big chapter, although it seems odd because it basically just covers two reactions of alkyl halides. They're called nucleophilic substitution and elimination, or sometimes called beta elimination. So those are going to be two halves of the chapter, and then we will tie it all together at the end. But the first several videos will be on nucleophilic substitution. These are reactions of alkyl halides in which a halogen gets replaced with something else, in other words, substitution. So this video will just serve as an introduction to that topic, and I would suggest that you study the introduction and pages 321 through 323. Again, alkyl halides undergo two main types of reaction: nucleophilic substitution, in which an alkyl halide, and here's the halogen, remember this could be chlorine, bromine, or iodine, and then it reacts with some nucleophile. We're going to have to define what that means. But basically it's any compound with a pair of electrons that wants to share with the carbon, so that it wants to form a bond with the carbon and shove the halogen out of the way. It may or may not have a negative charge, so I put that negative charge in parentheses. And you'll see the symbol again, the NU just stands for nucleophile. You end up with then the nucleophile attached in place of the halogen, so that's why it's called substitution. And it's nucleophilic because the thing it's substituting for the halogen is the nucleophile. Now if the nucleophile is negative, and it's replacing a negative halogen, then it ends up being neutral. If the nucleophile is neutral and it replaces a negative, then the nucleophile has to become positive at the end. So it's either neutral and becomes positive, or negative and becomes neutral. We'll see examples of all of those later. I know right now it seems a little bit nebulous, but that's the main idea, is that a halogen gets replaced with something called a nucleophile. The other thing that can happen with alkyl halides is if it has a hydrogen on the carbon next to the halogen, in other words, the beta carbon, remember this is the alpha carbon, this is the beta carbon. If it has a hydrogen on that position, then, and it reacts with a base, then that base can pull off the hydrogen, drop a pair of electrons in here to make a double bond, and push out the halide, and thus you get alkenes. So these kinds of compounds can be lots of different things depending on what the nucleophile is. The product of elimination is always just an alkene. And the halide goes off as what's called a leaving group in both of these reactions, and the byproduct here is whatever the conjugate acid of that base is. But what becomes confusing is that sometimes the same thing can be a nucleophile and a base, and we'll see that at the end of the chapter when we talk about putting it all together. So what do these two things have in common? Well, first of all, there's a leaving group in each case. Now, leaving group in quotation marks because in this case and throughout this chapter and 90% of the time when we talk about a leaving group, it's just a halogen. So the leaving group is the halide. It leaves with its pair of electrons and becomes negative. So that's what we mean by leaving group. It's a group that leaves with its pair of electrons. So this pair goes off with a halogen, or whatever the leaving group is. In this case, it's a halogen. Now again, that seems a little funny to call it a leaving group because it's not a group of atoms, it's just one atom, the halide. So bromine, a chlorine, or an iodine goes off and becomes chloride, bromide, or iodide, and that's true in both reactions. The other thing that's common in both is that you have this thing called a nucleophile and or a base, and those are essentially the same thing. In one case, the nucleophile wants to become attached to a carbon. In the other case, the base wants to become attached to a hydrogen, but they essentially do the same thing. They want to share a pair of electrons with something else. We're going to worry about elimination or beta elimination later on. Now I'm going to simply talk about nucleophilic substitution and just give you some examples because we'll learn a lot more about how it happens in the coming videos. But basically, here's some examples. This is N-butyl bromide, or 1-bromobutane. Turns out if you react it with different compounds that are hydroxides, like sodium hydroxide, potassium hydroxide, or whatever, that hydroxide can replace the bromide, and thus you get an OH on there. But notice it's not negative anymore. It's just an OH neutral attached to that carbon, and that gives you an alcohol. So here's a general thing. Alkyl halides react with hydroxide to produce alcohols. Here's another example, only in this case I didn't write it as SH-, I wrote it as NaSH, remembering that that really means a positive sodium and a negative SH, or SH-. That SH- is actually the nucleophile, and it replaces chlorine, in this case, to give you a compound that looks kind of like an alcohol, but it's got a sulfur hydrogen group instead of an oxygen hydrogen group. So this is what's called a thiol. The little prefix THI, sometimes THIO, means sulfur. So if you see thio in a name, it's generally a sulfur compound. Thiol means it's like an alcohol except sulfur. So here's the bottom line. SH- can react with alkyl halides to give you thiols. Here's another example. This time it's an iodide. This was a chloride, this bromide, but this one is an iodide. And if we react it with ammonia, now remember ammonia is a neutral molecule, not positive or negative, not ionic. So when it comes in and replaces the iodide, it stays there as NH3, but because now it has 4 bonds to it and it's donated a pair of electrons in, it becomes positive. So we end up with an ion called an alkyl ammonium ion. That just means it's got an alkyl group on a nitrogen with 3 other bonds so that it's positive, so it's called an ammonium ion. In this case, it's got 1 carbon group on it, so it's an alkyl ammonium ion. Here's some more examples. Here's a benzyl group. I don't know if you remember, but benzyl is a benzene ring with a CH2, so this is a benzyl group with an iodine. So this is benzyl iodide. If you react it with water, again a neutral nucleophile, the water comes in and replaces the iodine, but then it loses one of its hydrogens. So this is an additional step, as we will see in the mechanism. But basically because the product that you would form here by replacing the iodine with OH2 positive is a strong acid, it gives away its H plus and just becomes an alcohol. So let's go back and look at the previous one where an alkyl halide reacted with hydroxide to give you an alcohol. In this case, an alkyl halide is reacting with water also to give you an alcohol. The difference is in this case we had to take away one of those hydrogens from the water. Just in that taking away of the hydrogen comes after it's already attached to the carbon, not before. Here's another example, Ki on reaction with an alkyl halide. Well, again, this is potassium plus and iodine minus. Iodide, I minus, turns out to be a pretty good nucleophile, and it can replace the bromide and just become an alkyl halide. So in this case, an alkyl halide is becoming a different alkyl halide. You're replacing a bromine with an iodine. Again, we'll get details of all these reactions later. I'm just giving you examples at this point. Now, the third one on this slide is one that you already know about because we learned this way back in the alkyne chapter. Do you remember that if you start with an acetylide, which is an alkyne having a hydrogen pulled off the end and a negative charge, so this is called an acetylide, that those react with alkyl halides and replace the halogen with whatever the group is that's attached to the halogen. So here is what was the acetylide. This group attaches onto it, and so you get an alkyne. Basically, that's a way of turning a terminal alkyne into a longer alkyne. When we learned this reaction before, we learned it from the point of view of the acetylide, and we said you could alkylate it by reacting with an alkyl halide. Now we're going to learn the exact same reaction, but from the point of view of the alkyl halide, and it's a nucleophilic substitution because these acetylides are nucleophiles and they can replace the halogen. You may remember back when we learned this reaction that we said it works best if the alkyl halide is primary. That's true, and there's a very good reason for that, which we will learn later on. And that's the end of the video for today. Thank you.